Hello and welcome to this webinar on soil sampling and nutrient management for vegetable production. My name is Alex Dixon and I will be taking you through this presentation today. Today we will be covering the following topics: what limits a crop's yield, nutrient needs and interactions, vegetable nutrient guidelines, the nitrogen cycle and nitrogen testing. Let's start with what might limit a crop's yield. The image on screen is a yield map for a vegetable crop in Hawke's Bay. The mean zone yield is 75 tonnes per hectare in the red zones and 112 tonnes per hectare in the green zones. Overall, the yield ranged from 0 to 145 tonnes per hectare. This is a huge amount of variation. There are many factors that can limit crop yield. For example, soil structure, fertility status, and soil texture will all impact crop yield. Understanding what is limiting crop growth and therefore yield is important. Liebig's law of the minimum states that yield is affected by the most limiting essential nutrient. This is often shown as a barrel with shorter staves as shown on screen. The maximum yield allowed by the shorter stave, in this case water, sets the maximum yield that can be achieved. If water is limiting, adding more nutrients will not increase yield. The key point here in terms of crop nutrition is that the yield of a crop will be limited by a deficiency of any one essential element, even though all others are present in adequate amounts. Nutrient deficiencies in the crop can occur for a number of reasons, and adding more nutrient via fertiliser application may not fix the underlying problem. It may not always be an essential nutrient that is limiting crop growth and yield. There are other factors such as pH, soil compaction and drainage that must be kept in mind. For example, this graph highlights that applying more and more nitrogen will not compensate for water stress, or if it is too cold or maybe too wet, too hot or too compacted, the plant won't grow regardless of nutrient status. Adding more nutrient than needed is unwise. It will increase cost of production and not increase returns. It can even reduce yield. Adding more nutrient than the plant needs does not increase yield, and at high levels may even decrease yield quantity and quality. Any unused nutrients adds to the risk of leaching with negative environmental effects. This figure shows the relationship between crop growth, nutrient loss risk, and nutrient in the root zone for nutrients such as nitrogen. The pH conditions of the soil affect nutrient availability, and at either extreme, too acidic or too basic, plant growth will suffer even if soil nutrient levels are optimum. Optimum pH will vary for different crops, however, it should generally be between 5.5 and 6.5. If the soil is too acidic, so a very low pH, plant uptake of magnesium, nitrogen, potassium, sulfur, molybdenum, and calcium will be limited even if there are adequate levels in the soil. If the soil is too alkaline or basic, so very high pH, plant uptake of manganese, zinc, iron, and phosphorus will be limited despite adequate amounts being present in the soil. Where nutrients have the same biochemical uptake pathway, for instance phosphorus, iron, calcium and aluminium, their availability curves overlap, with the notched areas indicating uptake of one nutrient will reduce uptake of another. Nutrient uptake by plants is not an isolated process. There are interactions between the 19 plant essential elements. These relationships affect the ratio of nutrients taken up by plants and can be antagonistic, which decreases the availability, or synergistic, which increases availability. This is demonstrated by Mulder's chart on screen. The uptake of some nutrients antagonizes or blocks the uptake of others, for example, phosphorus and calcium, or potassium and nitrogen. Other nutrient pairs have synergistic relationships where the uptake of one nutrient increases the availability of the other, for example, nitrogen and molybdenum, or boron and magnesium. There is a variety of online resources you can use to help identify nutrient deficiencies in your crop. Yara's Check It app allows you to scroll through a library of photos of nutrient deficiencies in a variety of vegetable crops. Nutrient deficiencies can be addressed through foliar and soil amendments depending on the development stage of the crop. Nutrient Management for Vegetable Crops in New Zealand by Jeff Reed and Jeff Morton covers the most recent research into optimum soil fertility levels and fertiliser recommendations for vegetable crops grown in New Zealand conditions. Produced by Plant and Food Research for the Fertiliser Association and Vegetable Research and Innovation, it is available online. Chapters 1 and 2 cover an introduction to nutrient supply from the soil, fertiliser forms, soil sampling, managing soil fertility, environmental matters, and making nutrient recommendations. The remaining chapters cover specific crops and their specific nutrient requirements based on soil type, growing region, and expected crop yield. The basis of recommendations given is adding sufficient nutrient to ensure yield potential is achieved. To select the rate, you will need to know what is available in the soil and how much nutrient the developing crop will require. This will require you to have a soil test in the paddock before you grow the crop. Guideline recommendations rely on accurate and representative soil tests for nitrogen, phosphorus, potassium, sulfur, as well as pH, and you will need to know your variety's potential yield in tonnes per hectare, or for brassicas and lettuce, number of marketable heads per hectare. In this section, we will be discussing the nitrogen cycle. Our atmosphere is made up of nearly 80% atmospheric N, which is dinitrogen or N2. It is an important nutrient for making things like proteins, chlorophyll, hormones, and DNA in plants. Nitrogen in soils exist in many forms, but only a few can be taken up by plants. Soil microbes are important in changing nitrogen forms, making it available, otherwise known as mineralizing, or unavailable, otherwise known as immobilizing, depending on soil conditions. This is a dynamic process that will change depending on microbial activity and soil management practices. For instance, cultivation of soil will drive organic matter mineralization and therefore the mineralization of nitrogen, converting organic N into the ammonium form of N, which can be taken up by plants, or converted to nitrate N, which can also be taken up by plants but can also be leached. Leaching occurs when nitrogen is lost from the root zone. Plants predominantly take up N in two forms, either in the ammonium form or the nitrate form. Together these forms are added and described as mineral N. Nitrogen can be added to the soil in several ways, for example fertiliser amendments, animal dung and urine, decomposing plant litter, and atmospheric fixation through legumes like clover. Denitrification is the process of soil bacteria converting nitrate N into atmospheric nitrogen gas, or N2. It is important to note that incomplete denitrification will result in the production of nitrous oxide, or N2O, which is a harmful greenhouse gas. When urea fertiliser is added to the soil, there is a risk of volatilization, which is loss of nitrogen into the atmosphere as ammonium gas. This is driven by enzymes in the soil. Warm and windy conditions are drivers of increased volatilization. As discussed in the previous slide, ammonium and nitrate forms of N are plant-available forms and together are termed mineral N. Mineral N can be determined in two ways. The first is by sending a chilled sample to a commercial lab. This will have a week or so turnaround to get results. Alternatively, the nitrate component, which typically accounts for most of the mineral N present, can be assessed using the nitrate quick test method. The nitrate quick test can be done by growers or consultants. This is a reasonably cost-effective way of checking N levels very quickly. The rest of the tests need to be sent to commercial labs for analysis. If testing for nitrate, soil samples must be kept at about 4 degrees Celsius or soil microbes will continue to change the form of nitrogen in the soil. Do not freeze your samples. Make sure they are not sent on weekends or public holidays. Potentially available N, also known as PAN or anaerobically mineralizable N, is a test that can be used to determine how much N might be made available over the lifetime of a crop, i.e. how much nitrogen might be converted from organic form to mineral form. This test should be done before the crop is planted and is the test used by Nutrient Management for Vegetable Crop Guidelines to make nitrogen recommendations. This has commonly been the test of choice for cropping. However, the development of the potentially mineralizable test, PMN, or hot water extractable organic N test, which also measures what N might mineralize over time, has been found to be more accurate and will likely replace the PAN test as common practice. Total N can also be tested, however, this is mostly used for determining carbon to nitrogen ratios. Thank you for taking the time to listen to this presentation today. For more information, you can visit our website for follow-up information, including an online quiz and supporting information to this presentation. Please see our other video resources on how to do a basic soil test, how to collect soil for an N quick test at side dressing, and how to do a nutrient budget. Thank you again.